Good afternoon, everybody. My name is Richard Kemp-Harper. I'm Strategy Director at Arcola Energy. This is a webinar hosted jointly by Arcola Energy and our partners in this project, Ballard Power Systems. So the agenda we've got for you today is myself going to introduce the hydrogen fuel cell technology for refuse collection vehicles. And then Alan Mace from Ballard Power Systems is going to talk about the value proposition and the total cost of ownership analysis, which is the really interesting part, I think, you find of what we're presenting today. A story of not just what the technology can do, but actually is it affordable and the practicality of it. We're going to have then a local authority fleet perspective. It was going to be Eric Stewart, who is Head of Transport Services for Glasgow City Council. Unfortunately, for technical reasons and IT regulations and so on for Glasgow, unable to actually present the webinar. But Fiona Landy, who's been working with Eric for several years on the development of the Glasgow fleet strategy and for hydrogen, as part of that, is going to present Eric's slides on his behalf. And then after that, we've got a question and answer session, hopefully lots of responses from all of you to tell us then your questions. And David Yorke, who's Market Development Manager for Ballard, is going to run that session. There's a Q&A box in the bottom, so please put your questions as we're going through the webinar into that Q&A box, and David will pick those up and bounce them off the panel then as we go through. So yeah, please, all the way through, as things occur to you, do drop in what your questions are as we go. So I'm going to talk then about why we're looking at fuel cell and hydrogen for refuse collection vehicles. I think the interest of many of you here is going to be, how do we do zero emissions? Not so much why, because it's almost inevitable that we're going in that direction. But I think what we're going to present in terms of the fuel cell and hydrogen solution is something which is zero emissions, yes, but also in a way which is future proof, because this is a technology that's it's not an interim solution. This is something that can be robust for the long term, and the growth of hydrogen and fuel cell electric vehicles is only going to get greater over the coming years. The key win for this as a technology is we think it's a full service vehicle that is more or less a drop-in replacement for the diesel vehicles that are already in fleets, and a practical fleet level operational vehicle that is deployment ready to drop and go, if you like. But the key question, and this is what we'll spend a lot of time focusing on, is going to be, is it affordable? And we'll get to that as we go through this session. So an introduction then to how this project has come about. It's a joint effort between Ballard Power Systems, who have been developing fuel cell systems for 40 years. Ballard's been going, and they're the leader in terms of particularly this heavy duty market, with fuel cells in fleets of vehicles all over the world, with many hours of operational service. And then together with Ballard, Arcola Energy, we're a specialist in the powertrain engineering and the vehicle integration of this technology. And we're working in a range of heavy vehicles, buses, trucks, and trains to bring this technology to practical solutions. And so this project combines Ballard's experience and many years of understanding of the cost of fuel cells with our analysis of real-world vehicle applications and duty cycles, and understanding of actual data that we've captured from both local authorities and private organizations running commercial operations in this space. And together we're putting that as an in-depth analysis of the total cost of ownership and comparing that against battery electric. And we'll start to see the balance of the benefits and the costs as we go through this session. And I think one thing to emphasize is that we would like to see zero emission vehicles on the road. That's what we're all trying to achieve. There will be some situations where battery vehicles will work, and we will encourage people where that is the case to do that. we also think that fuel cell and hydrogen technologies make sense in a lot of scenarios, and we hopefully will able to help you understand where that makes the most sense and where the technology is the most suitable. So let's introduce the technology and talk through the various components. Let's start with what's in green there on this picture, which is the hydrogen tanks. We are putting 30 kilograms of hydrogen on the RCV, and that is, a roughly 500 kilowatt hours of energy. That is, the hydrogen is converted to electricity in the fuel cell, and together we think of that on the vehicle as the energy for the vehicle. So electrical energy from the fuel cell, from the hydrogen tanks. And the beauty of a fuel is that the fuel cell will run as long as there is hydrogen there, and you can fill that up in 5 minutes. So this becomes a really practical, flexible vehicle that's very like the sorts of operational practicality that a diesel vehicle is now. So the fuel cell and the hydrogen is energy. The power comes from batteries. So we've got small, high power batteries on this vehicle, and the batteries do all the hard work of the driving the wheels, providing that power, and the auxiliary power as well for the bin lift body and so on. And then there's an electric motor that turns that electrical energy, of course, into traction at the wheels, and similar for the auxiliary power systems. I'm sure you'll have more technical questions, but that's a very quick overview. But as you can see, the benefits then that you get at a vehicle level is because you've got that energy on board, a large amount of energy, you're not compromising the payload of the vehicle. As it stands, we're more or less equivalent mass of vehicle to a diesel now, and we expect to improve that over time with better integration. With that amount of energy on board, we're able to do a really long shift. So 12 or 16 hours is possible against the duty cycles that we've seen. And in some cases, that's probably 2 days between fills of hydrogen, depending on how vehicles are operated, or it can allow you to extend the number of shifts that are done or the length of the shift. Because we're using the battery for power, but we're not using it for energy, the battery keeps at a nice state of charge. So you get your full power from the battery throughout the shift. You don't get it dropping off towards the end. And because it's hydrogen, and you get fast fueling in under 10 minutes, as good as 5 minutes, depending on the interaction with the infrastructure. And we think that you'll see in Alan's analysis in a few moments that we've got a pathway to total cost of ownership lower than diesel and comparable to a battery electric vehicle. At a fleet level, the flexibility that this sort of full service vehicle can give you can help you reduce the fleet requirements. And you'll see that reflected in the sort of things that Fiona's going to talk about with Eric's slides. Fast refueling means that you're using the vehicle, high utilization, you don't have to stop your operations, just get on with the job. And this technology is going to give a longer vehicle lifetime, we think, than conventional technologies. So it could lengthen replacement life cycles and contribute to a really good total cost of ownership for the vehicles. And as I said, operations are very similar to what people are used to with diesels. So summarizing from a technology perspective, this is a zero emission refuse collection vehicle that is a practical offering in terms of being able to drop this into fleets as it stands. I think one important thing to emphasize is that fuel cell and hydrogen technology, particularly with Ballard's experience, is a proven technology. The components we're putting together are off the shelf, rehearsed and well robust technologies that have been used in heavy duty applications. So it's not a technology which is high technology risk. It's actually really solid and has been proven through many years. And so what we're showing here is really an analysis of the total cost of ownership to show that it's affordable and practical, as well as being a good solid technology. And I think one of the things we've brought to this is Arcola's experience looking at the duty cycles together with Ballard's experience and knowledge of the fuel cell cost profile, putting those things together is, for the first time, I think is quite an exciting development. So I'm going to hand over to Alan now, who's going to then present his view of the total cost of ownership and the details of the calculations we've gone through. So Alan, over to you.
Okay, great. Thank you, Richard, for the introduction to the work we've done, and thank you to the SOE for hosting this event and for all the attendees. So great attendance today. That's really nice to see. So as Richard mentioned, a fuel cell RCV is a one-to-one replacement of a diesel RCV for most applications. It's really a full-service truck, but we need to ask if it can compete economically. So a common practice here is to use, for these economic evaluations, is to use a total cost of ownership calculator to estimate and compare the capital and the operating costs of the different powertrain technologies. So for this study, we compared fuel cell and battery electric RCVs to diesel as a baseline. Diesel was our baseline there. So I'll take probably about 10 minutes here to explain the TCO calculator and some assumptions, some of the risks and results, and then we'll have an opportunity for Q&A after the final presentation, and keep the questions coming through the Q&A box at the bottom of your screen there. Just as background, there's already some first demonstrations of fuel cell RCVs operating in Europe. So some programs that are already going. So fuel cell RCVs are already being proven in daily operations. Okay, next slide, please, Richard. So for our analysis, we really need to start with an understanding of the typical duty cycles for RCVs. So Richard's team at Arcola did this by instrumenting a number of trucks in different fleets with data loggers to capture time, position, speed, elevation, and engine power. Different types of refuse collection routes were investigated, both what we refer to as an ARC duty cycle, which is, we think, characteristic of residential collection, where the RCV travels from the depot to the collection site and then makes a series of sequential collections until the bin is full, at which point the RCV then travels to the dump station and then returns to duty for another load. And the second type of route, what we refer to as a node duty cycle, is where the RCV travels from the depot to a location to make one or maybe a few collections, then travels to another location to again make one or more collections, and repeats this until the route is complete. This type of route is characteristic of commercial collections. We noted significant differences in how the trucks were used in these two different applications. The requirement for full payload and about 8 or so hours of collection time for the ARC duty cycle, whereas the node route requires longer hours. 12 hours per day was not uncommon, and maybe not necessarily full payload in that application. So Arcola used the data to build duty cycles. You can see a duty cycle in the top part of the screen here, to define the second by second power and payload requirements for the RCVs and the energy required to complete the required work. So now, once we have the duty cycles, engineers at Arcola built a computer model of the fuel cell refuse truck and simulated the performance of this virtual truck operating over those duty cycles. The simulations then guide the engineers in sizing and selecting the fuel cell engine, the amount of hydrogen to carry on the truck, and the powertrain components. And you can see here in the table on the screen, really how the vehicles were set up, the architecture for them. So now that we have the design of the fuel cell RCV and know how it will be used, how much fuel it will consume, now we can estimate the cost to own and operate that truck. Next slide, please, Richard. For the TCO analysis, there are some costs, such as insurance and taxes, which are considered constant across the different powertrain technology types. But between those different technologies, there will be significant differences in cost of the vehicles, maintenance, and fuel, including fuel infrastructure. So we included those costs in our analysis. We also evaluated the number of RCVs needed to complete the required shifts. And there's 2 points here to consider. First, if a truck cannot carry the required payload, for example, because the batteries are too heavy, then more trucks relative to a diesel fleet will be needed to complete that work. And then secondly, if the trucks need to be taken off duty for refueling or recharging during the shift, then additional trucks would need to be used to complete that work in the allotted time to avoid extending the shifts into overtime hours. We did not include the cost of labor in this analysis. So any labor cost for situations where additional trucks are required was not captured. And any inefficient use of labor, for example, because of poor vehicle performance or unproductive time during battery charging, that's a significant cost that should be investigated once the final fleet composition is defined. We did include costs of depot-based battery chargers and hydrogen fueling infrastructure, but we did not include the costs associated with en route chargers. And although it's understood that diesel and fuel cell trucks refuel in only a couple minutes and are therefore always ready to deploy on an emergency basis for urgent needs, we did not attempt to capture the costs associated with the long charging times and unavailability of the battery RCV during those charging periods, which could drive the need for additional, spare vehicles to respond to emergency situations. And then additionally, the lifetime of batteries in this application is unproven. We assumed the batteries would last between 4 and 8 years for the battery electric RCV, and that the batteries would last at least 10 years for the fuel cell RCV, since the fuel cell has the capability to better manage the batteries during operation of the vehicle. And those battery replacements result in a cost to the battery electric RCV of between about 1,700 pounds and 9,400 pounds per vehicle per year. So this table up here just shows some of the costs the cost ranges that we've used in this analysis. Okay, next slide, please, Richard. So when we look here at the TCO results, the fuel cell results are shown in the blue bar, battery results in the dark bar. On my screen, it shows as dark brown, and then the diesel in kind of the lighter brown color. The top 3 sets of bars, or the top set of 3 bars, is the total cost of ownership. So that's all the costs rolled up. And the next set of bars would be the CapEx cost of the vehicles, then followed by maintenance, battery replacement costs, and fuel operating costs. The size or the length of the bars indicates the cost range that we expect from each of those categories. And looking at the top set of 3 bars, our analysis shows that fuel cell RCVs can be on par or lower costs than both the battery electric and the diesel RCVs. And the fuel cell RCV, importantly, has a path to the lowest cost of ownership as the fuel cell costs start to approach the targets forecast by experts such as FCHJU, US Department of Energy, and others. The next set of bars indicates that fuel cell vehicles are right now more expensive. This is the CapEx cost, but like us, many experts forecast that costs will rapidly decrease in the coming years as the fuel cell industry starts to scale up and vehicle integrations improve. And we're already seeing those costs over the last, I would say, 5 to 10 years, really dramatically decrease. The next set of bars is for maintenance, and we foresee that maintenance cost of the fuel cell RCV is currently probably higher than the diesel RCV, but it will reduce according to a learning curve and become lower in cost to diesel, since the fuel cell solution is an electric solution with few moving parts, and it eliminates the costs of oil and lubricants. The pure battery solution is really the simplest architecture and has the potential for low maintenance costs, unless, of course, battery maintenance becomes an issue. The cost of hydrogen for this study was varied from a low of £3 to about £6 per kilogram. And you can see that savings compared to the diesel RCV are expected as the cost of hydrogen decreases. The fuel cell RCV can operate 16 hours a day or more with 30 kilograms of fuel. And so this introduces the possibility for completing more work with fewer vehicles and thereby further reducing costs. We didn't model this here, but that's a potential upside. And extending the life of the RCV to 15 years with a fuel cell rebuild at 8 years could again have a significant impact on reducing overall costs of the fuel cell fleet. And just a note that this analysis doesn't represent total costs, since labor and taxes and en route charging and some of those other costs are not included. So it's a view of the costs that we included, and there are other costs. Okay, next slide, please, Richard. Okay, so last slide here for me. I also wanted to mention that within the waste management business, there's other vehicle types, including, like you can see on this screen, yard trucks and transfer trucks. And we should consider those for conversion to fuel cells. And by adding these trucks into your emission reduction project, the scale of both the hydrogen station and the fleet are increased, which can contribute to lower total costs, because hydrogen costs typically reduce, those costs come down as the scale increases. And you can also amortize your fixed costs including infrastructure and maintenance investments over more vehicles. So in summary, fuel cell RCVs are full service with capability for full payload, long shifts, even back-to-back shifts without refueling. And because it takes less than 10 minutes to refuel your truck, your fuel cell trucks are always ready to be called into service when there's an urgent need. These factors can reduce the number of vehicles in your fleet. We believe our approach here is a conservative treatment of fuel cell RCV costs. And the reality will be that the many performance and operational benefits of fuel cell RCVs will result in even an improved TCO. And with that, I'll hand over the controls to Fiona Landy for a Scottish perspective on the role of hydrogen and fuel cells in public projects. Thank you.
Good afternoon, everybody. As you can tell, I'm not actually Eric Stewart. I'm standing in for him. Just a bit of background to Eric. Eric is head of transport services within Glasgow City Council, and he's brought a wealth of knowledge from his previous careers as the CEO of First Bus Glasgow and latterly Strathclyde Partnership for Transport. I first started working with Eric in my role at the Scottish Cities Alliance when I was leading on kickstarting the hydrogen economy across the 7 cities. So I've been working with Eric for around 4 years during that time when he was developing the fleet strategy for Glasgow City Council. And that's taken a complete holistic approach to really changing the way that they actually operate their fleets, trying to rationalise fleets. Obviously, decarbonisation is absolutely pivotal to that, but really making that step change from a very, very old fleet to a very new and modern way of working across depots and with a zero carbon mission in the focus. From the work that Eric's been doing as part of that strategy is looking at having intelligent depots, moving to more like super depots. Eric runs all fleet services, so clients are actually right across all the directorates in Glasgow City Council. So they manage all the fleets and the services for the whole entire new 2,000 odd vehicles. Part of the fleet is looking at the actual costs of actually moving to zero emission technologies, and it's not a cheap thing to be able to do. But however, during the transition to zero emission technologies, Eric has been looking at how they can rationalise the fleets, looking at particularly the heavy fleet vehicles, putting the stake in the ground that they'll all be fuel cell electric. And that's allowed him to start looking at rationalisation. As Alan has said, you have a much longer shift patterns. So then you start double shifting at the same time, so really driving those costs down. As I said before, Glasgow City Council's fleet was very aged. So the mission is now to really bring those vehicles down to below 5 years of age, looking very much at where they can save further costs in terms of shift patterns with their staffing as well. So really trying to transform everything they do within the council, whether battery electric for more their lighter vehicles, passenger cars and sort of the vans, and then very much heavy fleet vehicles with the jewel in the crown is the RCV fleet that is underway with Arcola Energy and Farrad Hill End. Before Eric joined the team, when they were procuring the refuse collection vehicles, there would be a minimum spec, I would say, around just what the vehicle has to do. And now that's moved to be very, very specific in terms of the technology. And you'll see that, what Eric has written here is building in the telematics. So at any one time, he will know where those vehicles are when they're getting up to full capacity to return to a depot that's near them, not back to base. And to really transform the way they actually use those vehicles. Glasgow had a year have something like 380,000 tonnes of waste to distribute and back into different waste bays. So yeah, quite a big operation. And of course, diesel is banned moving forward. As I mentioned about their fleet sizes, 1,400, but majority of those are heavy fleet vehicles. And there is a real drive by Susan Aitken, the leader of Glasgow City Council, to be the first net zero city in the UK by 2030. And the way they are operating right now, I think they can actually achieve that very much so. But also when we're trying to look at fleet rationalisation and the cost of actually changing your fleet, there is a very important message to actually get over to people, that there are over 300 deaths alone each year in Glasgow from the air quality issues and health. So it is a real must that, make that transition to zero emission technologies as soon as we can. And that goes in line with cities becoming decarbonised by 2030 as well, city centres. I think also there's an important message around when we're looking at fleet decarbonisation is, and we're working with Eric around creating that green pound. If you look at what it costs, maybe it's twice as much or 3 times as much for a zero emission vehicle compared to a modern diesel. We need to be looking at what's the impact on the health of your citizens and also on the NHS. So it's really trying to transform the way we do these calculations moving forward. There's one point, I suppose, is there within the council, there is this, some people within the council really prefer the battery electric side compared to the fuel cell electric. To be honest with you, it'd be much more about horses for courses. I know that Eric has put the stake in the ground that all the heavy fleet vehicles be fuel cell electric. But there was a couple of messages that came through with this particular gritter. And so not to use 12 hours between snowfall, which sort of really made the point to him that for some of their services, they really do need the hydrogen and fuel cell electric vehicles rather than battery electric. During my time with Transport Scotland, the Low Carbon Economy Directorate, we secured funding for Eric to make that first transition to fuel cell electric technology. But these particular vehicles are dual fuel, and they are produced by Ulemco in partnership with Cuthbertson's. So Cuthbertson's did the actual bodies for these vehicles to just allow the Glasgow City Council to start to get used to the technology, but always having that diesel backup because these are mission critical vehicles in the winter, obviously with the snow. But that was the first step for Glasgow City Council. So we're looking at refueling infrastructure at one of the depots at Gartcraig to actually start refueling these vehicles this year. So they'll come on stream later on. This is some of the vehicles that have been bought and are coming through this year. So as I said, battery electric, very much around the cars and the lighter vans, dual fuel gritters, and the temporary fuel in June. One electric RCV, which we're doing very short runs around certain areas of the city. And then obviously working in partnership with Arcola Energy and Farrad Hill End is this RCV, which we will have ready for COP26 for demonstration, which is really exciting. Then we will be moving to permanent hydrogen refueling infrastructure. It will be green hydrogen, and that's based at Glasgow City Council's big energy for waste depot at the Grec, which is called Polmedy, which is a fantastic area to have a depot of that scale, because down the road is First Bus Glasgow, and also we have Alstom further down the road, and it's also very accessible to other local customers who could be actually using that facility that we've actually been engaging with, who also want to be decarbonising with using hydrogen fuel cell technology. So in the future, we'll be looking at the tippers and tractor units as well. So there's quite a list within Glasgow City Council, which the vehicles that they would like to actually move over to fuel cell technology. I think one thing that's really important as part of this whole decarbonisation strategy for Glasgow City Council and the scale that they operate these vehicles at has really allowed myself to work with them and so partners, Arcola, BOC, ITM, Scottish Power, to really start to create that demand. So last year, BOC, Lindy, ITM Power, and Scottish Power signed a memorandum of understanding to actually build a 10 megawatt electrolyzer up at Whiteley, right, which is the biggest wind farm site in Europe. And that then allows myself, in the role of my hydrogen accelerator, to start really looking right across the region in terms of how we can start to redeploy these vehicles, not only RCVs, but we're looking at all the local authorities' vehicles, heavy fleet vehicles, and where we can make that transition to start replicating what we're doing in Glasgow right across other cities and regions as well. So it has been a massive step change in really going from a very novel, smaller projects that we've done in the past to really starting to get that scale up and start sector coupling, whether it's road transport with trains, etc. So really exciting opportunity there. The most important thing I would say as well is about building that Scottish supply chain. So through the work we've been doing with Arcola Energy, with Farrad Hill End, which is a Scottish-based company, and now we have Arcola Energy in Dundee, which is going to be fantastic. It's really allowing to make sure that we develop those high-skilled jobs. We're building up the Scottish supply chain. We're going to have some fantastic powertrain test facilities being deployed at Mission Scotland Innovation Park the next year or so, and that's going to be the home of sustainable mobility. So just by us all working together, we are really forging ahead with the decarbonisation of our transport sector, and it's very much important of that ecosystem for Scotland, and Glasgow is very much at the centre of that.
So the first question, I think, really to you, Alan, is what is the mileage of the RCV? I'm not sure whether you actually said that in the presentation or not, but just to reiterate that, if you could, please.
Yeah, so I think with and Richard can probably supplement my comments here. So, but I think some of the modeling that Arcola has done has shown that these RCVs can go well over 100 kilometers. It really depends on the type of route that they're on and whatnot. But, you know, a combination of 120 plus kilometers with more than 3,000 bend lifts. If there was less bend lifts, you could go longer distance. Richard, do you want to make any comments on that?
Yeah, I think it's difficult with an RCV to talk about mileage because most of its work is stop-start and it's more about time and length of shift and payload. But in the domestic collections, so the ones who would be familiar with that sort of distance that Alan's talking about, 120 kilometers comfortably, in the commercial operations where you're going further to sites and picking up some waste from retailers and then going on to other sites and then a longer run back, you're more efficient and faster speed. So you're probably doing more like 200 kilometers or more.
Okay, thank you very much. This next question is I guess to you, Richard. I don't think we need to go into details, but is what cooling requirements are required for the fuel cell and the batteries?
Yeah, so there are two different cooling systems. So one for the fuel cell system and the power electronics at running about 60 C, and then keeping the battery happy at around 25. So yeah, two separate cooling systems.
Okay. And maybe you, Alan, what is the lifetime of the fuel cells used in the RCV?
Yeah, so Ballard's been doing heavy duty, making and developing heavy duty fuel cell engines for 30, 40 years now. And during that time, the lifetime has improved, the performance has improved, energy density, cost has decreased. As far as lifetime goes, we've actually had buses that have operated in London on commercial routes in service for over 30,000 hours without replacing the fuel cell, without major maintenance on that fuel cell. So we actually, conservatively say, 25,000 hours of operation in a heavy duty environment for the fuel cell, and potentially 35,000 hours is achievable, and that has actually been demonstrated. So conservatively, we usually say 25,000 hours, though. Okay. And I guess I would just say too that that's a point that probably differentiates Ballard fuel cell systems from maybe some of the other fuel cell systems that are on the market that are those other products are maybe focused on other applications which require shorter lifetimes, and so maybe they're a lower cost fuel cell module, fuel cell engine, but again, the lifetime's shorter. We're focused on heavy duty applications, and so that's reflected in the long lifetimes. Thank you.
Okay, thanks. I'm going to wrap a few questions up to here because there's a few questions on the hydrogen production. So first of all, what's the color of the hydrogen production? Grey, blue, or green? And for those of you who don't know, hydrogen, if it's produced with a carbon, so in a mixed carbon, it's generally referred to as grey hydrogen. If there's carbon capture and storage of some description, you normally refer to that as blue hydrogen. And if it's made from a renewable energy source, we normally refer to that as green hydrogen. So what type of hydrogen is used, and what methods of production for hydrogen do we say is okay? And it might be worth if Fiona as well can answer on this about what's happening in Glasgow. So I don't know who wants to take that up first, and if anyone else has got any comments on that.
So if I take that, David, and then I'll pass it on to Fiona. So my view is from the people that we've spoken to, there are two drivers for zero emissions. One is improving air quality, and particularly RCVs on city streets, that's important. But the other is clearly for councils, it's decarbonisation. So it has to be a low carbon source of hydrogen and has to be green, essentially. And all the customers we're talking to are saying green hydrogen, renewable energy into electrolysis. And I think, handing to Fiona, that's clear in the Glasgow strategy that that's the objective.
Yes, thanks, Richard. Very much so. I mean, Scotland has the right ingredients. We have plenty of wind and plenty of water. So green hydrogen is very much top of the agenda. During my work when I was in the Scottish Cities Alliance, kickstarting that hydrogen economy across the 7 cities, it was always about green hydrogen. So yeah, that is the focus.
From the fuel cell perspective, the fuel cell, it doesn't care where the hydrogen comes from, as long as it meets the standards, the quality standards. The fuel cell doesn't really care.
A very good question here, and it's been sort of asked in a number of ways. Is what regulatory checks must be undertaken on either the hydrogen and or the electrical system on the vehicles? And basically, are there any extra checks? And if I can expand that a bit, because we've had a couple of questions on safety of the vehicle, which is a fair enough comment when you're talking about hydrogen. And we've had another question as well on maintenance and what maintenance needs to be done, what training for technicians, and modifications to the building. So if I can kind of lump all those three together, because I think they're all basically safety related questions, and I'll offer that one open to who wants to take that one up.
So from Arcola's point of view, I'll definitely happy to take that one, David. So as Arcola Energy, this is, I guess, what we do as vehicle integrators, and we've got a key focus on quality and safety. There are the usual vehicle regulatory checks that you go through. We're working closely. We've got a team of engineers focused on the homologation of the safety case, and working closely with the vehicle certification agency on those checks and what they look like. And because this is relatively new technology, helping set those standards and define what those are. So much of it is already established standards that are now international. So for the hydrogen system, there is international standards. For batteries and so on, there are international standards that are now brought just into the vehicle development world. So that is all covered, and the vehicles, in our case, will go through a full approval process to be safe on the road. In terms of the broader safety piece, David, refueling is very safe, and there's a little training just to get used to it, but it's actually arguably cleaner and safer than conventional fuel is, because there's no chance of spills or so on because of the way the technology works. Maintenance, one of the things we're keen to do is to support local teams in the skills they need to learn these technologies. Again, it's a cleaner environment in many ways. There are hazards around high voltage battery systems, same for electric vehicles. There are some concerns and things to manage around hydrogen, but again, it's relatively easy to understand, and we're used to doing this, what the depot requirements are, what hydrogen sensors you might put in place, make sure there's plenty of ventilation and those to allow servicing of vehicles. So the disruption, I think, isn't too great. There is a transition to be made, but actually we expect that a lot of the maintenance and servicing will be able to be carried out by established teams of people with appropriate training. There's some specialist work around the fuel cell and the high pressure hydrogen system that would be done by experts such as ourselves in the short term, but the day-to-day maintenance can be carried out by the usual staff. Does that cover most of those, David?
I think that covers most of it. Yeah, I mean, if one of these vehicles is being taken on by an operator, full training would be given. I think that's fine to say. Having looked after hydrogen fuel cell buses for a number of years, it's not as onerous as it sounds when you listen to something like this. A couple of questions for you then, Alan. I'll try and lump these two together. We've got a lot of questions. Are the CapEx acquisition costs provided in the TCO model for the battery and fuel cell RCV representative of current market prices in the UK at this time? And then as a supplementary to that, what factors influence high-end cost estimate for fuel cell RCV? So does that make sense?
Okay, so first, just to address the CapEx cost of the fuel cell engine, we'll call it. Yeah, if you look at the TCOs, the results there, the high end really reflects probably the current pricing right now in the current volumes. You know, if we're talking about delivering tens of fuel cell engines, that's I think a fair price. As if we were talking about higher volumes, though, the price would certainly be lower, and that's I think the projection for the future is as we can consolidate demand, build volume, build the manufacturing, bring in more advanced manufacturing techniques, the cost is really expected to continue to decrease dramatically. As far as the full vehicle goes, I think the question there is, does the vehicle cost that is reflected in the TCO, does that reflect current RCV vehicle costs? And again, that's the case. Yeah, that's accurate. We've tried to take current costs of hydrogen cylinders, current costs of batteries for these RCV vehicles, and we actually modeled a more advanced battery for the RCV vehicle, which is higher cost than what we modeled for the battery electric RCV. And so we've tried to wrap all those costs up into the RCV cost. Yeah.
So a question here, I'll give this to Fiona first, and then maybe Richard, you could comment. But what percentage of the RCV market do you think would be better suited to fuel cell vehicles compared to battery electric vehicles? And it says several UK local authorities have successfully deployed battery electric RCVs, and they've been a proven fit. But not all duty cycles have been demonstrated. So if you could answer that from your side, Fiona, as a sort of end user side, and then Richard, if you could just comment on the end, I think it would be useful. Thanks.
Yeah, no, thanks, David. It's quite difficult to actually comment and say, to be honest. It all depends on your duty cycles and your payload. For Glasgow, for instance, the amount of waste that they actually have to move every single day, and the type of hills and everything else, topology they have to go through, they really need fuel cell electric that can actually carry out the full shift for actually moving that waste around. So it all depends, I would say, maybe 60%. It depends on what's the city or rural economy is actually like. To be honest with you, it's hard to actually give a definite answer on the percentages wise. Definitely, it all depends on what the shift is and what they're actually trying to move in terms of waste.
Okay, thank you. And Richard, do you have a quick comment on that?
Yeah, I think the commercial operations that we looked at, we're doing high speeds, long distances between the pickups, and there is, you would have to double the size of battery on the current sorts of vehicles to be able to do those routes, and that would lose a couple of tons of payload. So just not possible. So all of that section, I think, if it's zero emissions, is fuel cell. And then, as Fiona says, there are significant tranches of the domestic urban collection that also have high duties. And I think that extends if you are saying, actually, I want to reduce the number of vehicles, I want to get better asset utilization, I want to use longer shifts, the sort of things that Fiona and Eric's slides were showing in Glasgow's plans. And I think a zero emission vehicle that's a bit quieter than diesel might allow greater hours of operation and allow that fleet reduction. So once you take those factors into account, as Alan said, the flexibility of the vehicle allows you to do more. So actually, yeah, you could do existing short duty cycles with battery electric, but actually, why would you if you can do a better job?
Okay, thank you very much. And I'll be cruel and give this one straight back to you, Richard. Which are a couple of questions about the auxiliary equipment and the hydraulics is how do you manage the intermittent but very high power demand of the auxiliary equipment, and how much, and what's the division of power consumed by the propulsion as opposed to the auxiliaries, the hydraulics?
Yeah, so our way of dealing with the hydraulics is we add an electric motor to the hydraulic pump, essentially. But that gives you really fine-grained control then of spinning up that motor to drive particularly the compaction events inside the body of the RCV. And yeah, you run that hydraulics at the same power that an engine would, but you only run it when you actually need it. So you're actually saving a lot of energy with that electrification of it, and a lot more efficient. I think electric power takeoffs have shown about 30% fuel savings in a diesel truck. So we'll see that efficiency benefit. In a domestic collection, about a quarter of the energy is the bin lifts and the body energy requirement. But in the commercial routes where you're going further and farther, then the traction energy is more dominant.
Yeah. I'm just trying to squeeze in another couple of quick questions, and this one's a very good relevant one, which I'll pass to Alan first, and then you, Richard. But does an RCV use type create any specific issues with engineering of the fuel cell maintenance or the maintenance generally? I'll add in, particularly because they operate in dusty, sort of dirty environments, etc. So their operating conditions can be quite harsh. Have you got any comments on that, Alan, quickly, and then Richard?
Yeah, so real quickly, fuel cells can be sensitive to air contaminants because they consume air. And so in the fuel cell, you actually have a particulate air cleaner, and then you have a chemical air cleaner also. And the particulate filter can be changed at higher frequency, if it's a super dusty environment. And then as far as maintenance goes, you know, those air cleaners typically have some kind of a visual indicator on them, you know, if they need to be changed. So, Richard, anything else?
Yeah, I guess the main operating challenge for an RCV is the extremes of you're driving to dump the load at relatively high speed down to your recycling depot, but then you'll stop-start all day picking up the bins in front of people's houses. And that's, as an engineering challenge, is difficult. It's one reason why a diesel RCV is really inefficient, is because it's not good at that stop-start zone. An electric drive, and this is true of battery electric and fuel cell electric, is much better at managing that stop-start. You've got torque at low speed, and you capture regen as you're braking as well for efficiency. So the shift to electrification generally is good for that, for the RCV and in that stop-start type of operation.
Yeah. And then we've had a number of questions. Just one quick final answer. Again, sorry, Richard, I think this comes to you, about the position of fuel cell RCVs. When will we basically see them on the road?
Well, as Fiona pointed out, we should have a demonstrator vehicle with Glasgow ready for November for COP26 to be shown off there. We are hoping we'll have a fleet of vehicles on the road next year. And certainly from our point of view, very interested to talk to people about what the requirements are for vehicles in the coming year, because we'd like to add to that order pipeline. So the time it takes for a hydrogen project to get off the ground, now's a really good time to start having that conversation about what that looks like, what requirements are. And very much why we're having this conversation now is to kick off those discussions.
And David, sorry, can I just one point on that? Just working across the local authorities, you know, if there's opportunities to actually do joint procurement, you know, looking at RCVs, which is a jewel in the crown for any local authorities, there's the opportunity to really drive down the price of those vehicles as well. So that's an important area that we're working on as well.
Okay, thank you very much. Well, I'd like to thank all the panelists and the SOE for hosting this. Just to mention that we've got a white paper on this, which is available on both of our Arcolas and our website. So I think it's going to go in the chat, the websites, but arcolaenergy.com or ballard.com, where you can get a copy of the white paper. I'd like to thank you all for listening. I hope you've enjoyed the webinar. Again, I'd like to thank our panelists. And now I'll pass you back to Oliver of the SOE.
Hi everyone. Well, yeah, just really to echo those sentiments. Thank you, Fiona, David, Richard, and Alan for your time. That's been a really fascinating overview of the subject, and the questions were coming thick and fast. So I'd like to thank you all, and hopefully see you all again. So thank you very much.